Repeating again that this is a complicated topic, but we will just make a very brief introduction to the dynamics of cumulus and cumulonimbus convection. So going to our basics, here is the dry adiabat. As we said, as the air parcel rises from near the surface, it will act as a dry air parcel till the water in the parcel begins to condense and it reaches saturation at the condensation level. Above that, it begins to follow the wet adiabat, but it's constantly mixing. So now we are getting a little bit away from the simple arguments we made before about adiabatic processes. We said the parcel moves so fast relative to the environmental motions that it doesn't mix much heat with the environment. But the convections, whether it's cumulus or cumulonimbus, can be so vigorous that actually they create a local recirculation, and there is something called entrainment and dilute plumes and convective momentum transport, and all sorts of detailed processes exist. But the simplest way to think about it is that the parcel wants to follow the wet adiabat in a pure pseudo-adiabatic process. Why pseudo? Again, because water can condense and release heat within the parcel. But it repeatedly mixes with the ambient fluid, which reduces its buoyancy. Okay, so you can see that here is the wet adiabat, but here is the actual path, and this is the top of the cumulus cloud, cumulus convection, and it occurs somewhere at the level where the adiabat first runs parallel. So it's bending this way. This is the ambient adiabat that the parcel actually follows because of this mixing. You can see that the moist adiabat is parallel to the wet adiabat shown here. There is mixing, so it goes back to the ambient, and then it rises again somewhat parallel to the moist ascent along the wet adiabat, mixes, parallel, mixes, and so on. So the top of the cumulus basically happens where there is a steady achievement of accomplishment of so the parcel achieves a parallel to the wet adiabat, and then eventually obviously the two will come together as you go above where the humidity is basically reduced to very low values because the temperature has dropped off. So you can see the temperature is decreasing as you go in height away from the surface, so you're eventually going to bring the wet adiabat back to the ambient adiabat that exists with all these detailed processes. So it's kind of very quick introduction, and you can look at the vertical motion in the cumulus convection in terms of the height change that happens and the temperature change that is associated with the parcel movement. So it's again this idea of changes in potential energy conversion to kinetic energy and so on. So W is basically the kinetic energy, and the lifting of the parcel with its water vapor and condensation is the potential energy, right? So these scaling arguments, obviously we are not going to go into the details, but using the experiment, the water table experiment that we looked at, and data from the real world, you can compute the scaling of W squared comes because of, again, motion being induced in all three directions, and half W square being the kinetic energy, the potential energy being delta Z delta T over T. Okay, how much density change and is associated with the height change that results in the potential energy change that is converted to the kinetic energy that causes the vertical movement. So the heat transported is again proportional to the reference density. Because you have vertical motions over a certain scale, you use a reference density. W and delta T is the amount of heat that is being moved, amounts to approximately 1/2 of 2/3 alpha G delta Z to the half, and delta T to the 3/2. Okay, okay. So again, approximate numbers of 200 watts per meter squared from the estimates in the book. Change of 0.1 K is typical, resulting in vertical motion of 1.5 meter per second. This is in a cumulus convection. Obviously, you expect much larger changes in cumulonimbus. So here, looking at the zonal mean meridional cross section as an annual mean for the top panel. So you take all the longitudes in average from the surface to the top of the atmosphere, and you look at pole to pole. So you're going from 90 south to 90 north. This is called the meridional section along latitudes, and this is the height. So you averaged all the longitudes, right? And you're looking at the boreal winter season. December, January, February is typically the boreal winter season. June, July, August is considered the boreal summer season. And you can see the difference in the vertical structure of the zonal winds. You can see there is a top heavy structure here. Okay, these are the jet streams that we'll come back to later on. So there is a vertical shear here, so we'll do large scale balance and see how this vertical shear in these two blobs comes about. Those are the zonal wind maxima, and you can see there is a seasonality here. So this, in the winter it's maximum strongest here, in the summer it's the strongest here. Sun moves back and forth, energy moves back and forth, so the ITCZ, intertropical convergence zone, moves then back and forth, and so on. So the seasonality is very clear here. So in the boreal summer you expect convection to the north, ITCZ to the north, so you can see there is strong winds here. So using similar arguments, you get now vertical velocities of 25 meters per second in cumulonimbus convection, okay, with a change in delta T of 1 Kelvin over about 10 kilometers. That's a lot of energy being pumped up into the atmosphere. So obviously the hydrostatic balance doesn't have much meaning when you have such strong vertical motions. But the main thing to remember is that these are very narrowly confined vertical motions, and the large scale environment remains in hydrostatic balance. So we have to always remember that when we do our parcel versus environment type of calculations. The typical structure of the cumulonimbus convection, we talked about the anvil and the cloud base that's here, and there is this is typically happening in a moving system, right? So you can think of it as a cumulonimbus storm moving with the mid-level winds. Mid-level winds are somewhere here, surface winds are facing this way, they change direction, and the upper level winds are facing this way. So the convergence feeding the cumulonimbus convection is happening on the front end. So as the storm is moving, moisture convergence is happening, but the upper level winds are pulled down by the heavy rain. This is how the upper cold air, downdraft of the cold air happens. So when the thunderstorms pass, typically you might feel cool air associated with the rain, especially in the monsoon regions. Okay, so there is a feeding of the mid-level, and then there is the anvil being created by the upper level winds. So there is a squall point which moves, it's a stagnation point relative to the storm. So the storm is moving at some speed, and it has a stagnation point where there is obviously convergence of moisture and downdraft. So you can see this is kind of an idealized structure, but it's a composite of many events. So this is essentially what happens. So there is strong updraft, there is strong downdraft, and there is this complicated circulation. So this is a monster which has enormous amount of heat energy being released. So obviously it creates its own circulation. This is kind of a very simple explanation for very complicated processes. So you must read more if you want to follow up. This is just an introduction. Okay, I want to emphasize that because we have basically run through the scaling arguments to just show what are the values of typical vertical motion you get in cumulus convection versus cumulonimbus convection. If you get the idea of how vigorous and how complicated the cumulonimbus convection is versus cumulus convection, then you've got something out of this module.